electron neutrinos, muon neutrinos, and tau neutrinos. And in the very successful standard model of particle physics, neutrinos are assumed to have no mass. However, I want to say that physicists have been asking neutrinos really have no mass. Therefore, in the history, physicists have been studying various ways on neutrino mass. Now, I want to move on to atom-sake neutrinos. Well, as you may know, cosmic ray particles enter into the atmosphere from somewhere in the universe. And cosmic ray particles are, say, high-energy particles. Most of them are protons, some of them are helium nucleus, and some of them are even iron nucleus. And these cosmic ray particles, once they come into the atmosphere of the Earth, they interact with the air nucleus, and typically they produce, well, these interactions produce pions, and then these pions decay to muons and then to electrons. And during this decay chain, neutrinos are produced. And in fact, about 50 years ago, these neutrinos produced by cosmic ray interactions were observed for the first time. In 1965, atmospheric neutrinos were observed for the first time by detectors located very deep in underground. One experiment was carried out in South Africa, here in India. And these experiments successfully observed atmospheric neutrinos. So we know atmospheric neutrinos for more than 50 years. But I have to say that after the discovery, people did not pay much attention to atmospheric neutrinos. Now, atmospheric neutrinos got some interest in the 80s. So I want to talk about the more recent history of atmospheric neutrinos. In the 1970s, grand unified theories that try to unify strong, weak, and electromagnetic forces were proposed. And these theories predicted that protons should decay with the lifetime of about 10 to 30 years. Well, of course, 10 to 30 years is a very long lifetime. Therefore, well, proton lifetime has nothing to do with our daily life. But, well, people thought that this prediction was very important for understanding particle physics. Therefore, several experiments began in the 80s to observe proton decays. And these are the experiments that began in the early 80s. Kamiokande was constructed in Japan. IMB was another large detector in United States. KGF was an experiment carried out here in India. Nusex and Frejus were constructed in Europe. And these experiments observed many contained atmospheric neutrino events. And in fact, these were the backgrounds for proton decay searches. And, well, as I said, there were several proton decay experiments, and one of them was the Kamiokande experiment. It was a 3 kiloton water Cherenkov experiment. Its dimension was about 16 meter in diameter and 16 meter in height, and it was located about 1 kilometer deep underground. And this detector observed relativistic charged particles by observing Cherenkov radiation radiated by relativistic charged particles. And the Cherenkov radiation is observed by photodetectors instrumented at the detector wall. Therefore, if a particle propagates in the water, then the experiment should observe a ring pattern of light. And if a proton decay occurs, then the detector should observe 2 or 3 Cherenkov rings with the back-to-back configuration. So this was the experiment. But maybe some of you may not know where is the location of the experiment. So I want to tell you. Well, okay. Well, the experiment was carried out here, and the location looks like this at this moment. And you notice that there should not be much human activity, but then it will be very difficult to do experiment. Well, fortunately, there are some human activities, and in fact, there was a mine activity, mine company. So the Kamiokande experiment was constructed in an active mine. And this photo was taken in the spring of 1983 when we constructed the Kamiokande experiment. Well, in fact, this photo was taken when Professor Koshiba, who was the spokesperson of this experiment, came to Kamioka in a day. And well, we took a photo, and you can see Professor Koshiba in the middle, in the front, and also you see several other young students behind Professor Koshiba. Well, one of them is me, and in fact, we worked in underground for several months to construct the Kamiokande experiment. And I said that the Kamiokande experiment was constructed in active mine. And in fact, every morning we took a mine train to go underground. And well, this was indeed a photo of the mine train we used. And in the mine, well, we constructed the Kamiokande experiment. This photo shows our work. We installed photodetectors onto the detector wall. But as I said, Kamiokande detector was 16 meter high. Therefore, we thought it's non-trivial to install the photodetectors to the 60 meter high place. Therefore, we decided to use rubber boards in order to install photodetectors. Well, of course, the working condition was not so good this way. We worked this way. Anyway, our construction was successful, and we began the experiment in July 1983. But unfortunately, we didn't observe any proton decay. Instead, we observed background events. They were atmospheric neutrino interactions. So, well, at the beginning, it was not so difficult to find out the proton decay signal but with time goes on, we have more and more backgrounds. Therefore, at some point, we had to improve our software in order to better separate the proton decay signal and atmospheric neutrino backgrounds. So, 3 years later, in 1983, I began to improve the analysis software in order to improve the proton decay searches. Well, we wrote several new analysis software, and as a test of the new software, the neutrino flavor, that is nu-e or nu-mu, was studied for the atmospheric neutrino events. Well, this was purely a test of the software, but it was found that the number of muon neutrino events was much fewer than expected. As I said, this was a test of the software. Therefore, this result suggested that there must be something wrong in the new software. So, we had to find out what is the mistake. So we started various studies to find mistakes in the analysis software. Well, in fact, we even studied the simulation software or even the data reduction software. Anyway, we really wanted to find out the mistake. By the way, this is the one of the observed events in the Kamiokande experiment. Here, this is most likely a muon neutrino interaction. And the problem was, this kind of event pattern was much fewer than expected. Anyway, we studied to find out what is the mistake. And we studied for about 1 year, but we didn't find any mistake. Therefore, we concluded that muon neutrino deficit cannot be due to any major problem in the data analysis nor the simulation. Therefore, at this point, we decided to write a paper on this data. In fact, this paper was a rather simple paper. We simply reported the number of observed muon neutrino events in the Kamiokande experiment. That was 85. We also mentioned the number of expected muon neutrino interactions at that time. That was this much events. And also we reported the number of electron neutrino observed and number of expected electron neutrino interactions. So it was clear that there was a huge deficit of muon neutrino events. And at that point, honestly speaking, we were not sure what was the cause of the deficit. But anyway, this was the data, and I thought that the result was really unexpected. And we had no clear idea what was the cause of the deficit. But I thought that it was really important to find the cause of the deficit. And therefore, I decided to concentrate on this problem. But well, although we published this data, for several years, we had no support from the other experiments. it was only in 1991, the other experiment, the IMB experiment in the United States, reported the similar data. IMB experiment was another large water Cherenkov experiment. And this is the summary of the Kamiokande and IMB experiments on the deficit of muon neutrinos relative to the electron neutrinos. So both data are quite striking. The deficit of muon neutrino is very significant compared with the no deficit case, that is, should be around 1. Well, okay, that was the data. And in fact, with this data, we were unable to conclude what was the cause of the deficit. But honestly speaking, from the beginning, we thought that maybe it was due to neutrino oscillations. This was just a possibility. Anyway, I mentioned neutrino oscillations. Therefore, a little bit about neutrino oscillations. Unfortunately, I'm afraid I cannot go into detail of the mechanism of neutrino oscillations. I just tell you what will happen if neutrinos have mass. If neutrinos have mass, neutrinos change their type or their flavor from one type or one flavor to the other. For example, muon neutrino could oscillate to tau neutrinos. And here in this graph, I show you the oscillation probability. Suppose a muon neutrino is created at this point, then if they begin to propagate in the vacuum, then the probability that muon neutrino to remain muon neutrinos go down, but if they travel further, this probability go back to unity. If they travel further, the probability goes down, go up, goes down. And if you ask what happens if muon neutrino survival probability is low, then the answer is at that time tau neutrino is appearing. So this is the neutrino oscillation, and this was in fact theoretically predicted by Maki, Nakagawa, Sakata, and Pontecorvo already more than 50 years ago. So we thought maybe, really maybe, neutrino oscillations could explain the atmospheric neutrino deficit. However, at that point, neutrino oscillation was one of the possibilities. We really wanted to find out the real solution to the deficit of atmospheric neutrinos. So we thought, what will happen if the muon neutrino deficit is due to neutrino oscillations? I said that cosmic ray particles enter into the atmosphere, and of course these cosmic ray particles enter into the atmosphere everywhere in the Earth. Therefore, atmospheric neutrinos are produced everywhere on the Earth atmosphere, and some of them are produced just above us. Then, well, I said just above us, but well, I would say 10 to 20 kilometers above us. Then these neutrinos come to the Kamiokande or super Kamiokande detector after traveling only 10 to 20 kilometers. Therefore, these neutrinos may not have enough time to oscillate. Now, atmospheric neutrinos are also produced in the other side of the Earth. And these neutrinos have to travel long distances. Typically, they have to travel 10,000 kilometers. Therefore, they travel long distances and they may have enough time to oscillate. Therefore, we thought that we should observe the up versus down asymmetry of the atmospheric mu neutrinos. If this effect is observed, other hypotheses cannot explain the deficit of atmospheric neutrinos. Therefore, if this is observed, that is the evidence for neutrino oscillations. Well, however, the Kamiokande 3 kiloton water Cherenkov experiment was, I would say, too small to observe this effect. We needed much larger detector. That was the super Kamiokande detector. Now I want to move on to the discovery of neutrino oscillations in super Kamiokande. In fact, super Kamiokande is a much larger version of the Kamiokande experiment. It is a 50 kiloton water Cherenkov detector whose diameter is about 40 meter in diameter, whose dimension is about 40 meter in diameter and 40 meter in height. And well, it is about, say, 20 times larger than the original Kamiokande experiment. By the way, it is an international collaboration, and at present we have about 160 collaborators from 10 countries. Now, before discussing the results from super Kamiokande, I want to mention the history of the super Kamiokande experiment. In fact, super Kamiokande has a long history. Already in 1983, super Kamiokande was discussed in a workshop in Japan. Well, the initial idea was like that. In the fall of 1983, Professor Koshiba recognized that the solar neutrinos could be detected in Kamiokande. He recognized that the Kamiokande detector was so good. Therefore, with the little improvement of the original Kamiokande experiment, Kamiokande should be able to observe solar neutrinos. And in fact, at the end, 1989, Kamiokande observed solar neutrinos. But, well, at that time, at the same time, he thought that the event rate of solar neutrinos that can be observed in Kamiokande was too few to study details of the solar neutrinos. Therefore, in 1983, he proposed super Kamiokande to study solar neutrinos and the other physics in detail. So, that was the initial idea of super Kamiokande. Then, 8 years later, 1991, super Kamiokande experiment was approved by the Japanese government, and the construction was, construction began in 1991 and finished in 1996. And in fact, the last 1 year was the installation of the photodetectors into the super Kamiokande tank. And of course, super Kamiokande is much larger than Kamiokande, and therefore we needed much larger number of people. And this photo was taken in the spring of 1995 when we constructed the super Kamiokande detector. Essentially, every day, these numbers of people worked in underground to construct the super Kamiokande experiment. And in fact, we worked hard, and we worked for almost 1 year. And in January 1996, we essentially finished the construction of the Super Kamiokande detector, and we started filling the detector with pure water. This photo was taken from the top of the Super Kamiokande detector, watching below, and you can see pure water was already filled to almost half of the detector. And the experiment began in April 1996. And in fact, since we had the experience with the Kamiokande and IMB experiments, the detector worked quite well from the beginning. And from the beginning, we observed these atmospheric neutrino events. This is a typical electron neutrino event, and this is a typical muon neutrino event. And we observed these atmospheric neutrinos every day. The event rate is about, say, 10 events per day. And well, of course, we knew that atmospheric neutrinos should be a very important topic for Super Kamiokande. Therefore, in the Super Kamiokande collaboration, we worked together as a team to analyze these atmospheric neutrino data. And in fact, we finished the initial round of analysis in 2 years, and we were able to present our first major results in 1998 at the Neutrino conference. And this is one of the transparencies that was shown at the Neutrino conference. And in fact, well, although this is a handwritten presentation, but this was in fact very important, and I want to explain. Well, the lower part of the presentation is for the muon neutrino interactions, and the horizontal axis shows the arrival direction of neutrinos. Cosine theta 1 means downgoing neutrinos. They just came just above us. And cosine theta minus 1 means neutrinos coming from the other side of the Earth. And these pluses show data, and these boxes show the expectation without neutrino oscillations. And you can see in the data there is a huge deficit for upward going neutrinos, almost a factor of 2 deficit compared with the no oscillation prediction. And this is what we expected for neutrino oscillations, namely muon neutrinos produced in the other side of the Earth oscillate to tau neutrinos, then go back to muon neutrinos, tau neutrinos, muon neutrino, and so on. Therefore, when they arrived at the Super Kamiokande detector, the probability that muon neutrino to remain muon neutrino is only 1/2. So this data clearly showed evidence for neutrino oscillations. By the way, this is purely our scientific presentation. However, we were honored to hear President Clinton's talk at the MIT's 1998 commencement. In this talk, President Clinton mentioned the Super Kamiokande result. And well, this talk itself is a long talk, therefore I just want to tell you the relevant part to neutrino oscillations. Okay, here it is. I just read. Just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. So, this talk was made just one day after our announcement of neutrino oscillations. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest subatomic physics, subatomic particles, to how the universe itself works, and indeed how it expands. Well, I think it was really an honor to hear this kind of talk from the US President. Anyway, this President's talk suggested that, in fact, small neutrino masses are very important. Therefore, in fact, of course, we physicists understand, and therefore, we have the neutrino oscillations. For example, the discovery made in Super Kamiokande was mu neutrino to tau neutrino oscillations. And since then, these experiments studied neutrino oscillations. And some of them observed atmospheric neutrinos, and some of them produced muon neutrinos based on accelerator beam and observed neutrinos in far distances. And all of these experiments clearly observed neutrino oscillations. But well, in this talk, I want to concentrate on our studies. So let me introduce more recent studies in Super Kamiokande. First of all, even after 1998, Super Kamiokande has been taking data continuously, and we have been improving the data statistics substantially. In 1998, when we announced the discovery of neutrino oscillations, the number of events plotted in this plot is 531 events. But if we make the same plot with the most updated data, the total number of events is almost 6,000 events. So our data statistics have been improved by more than a factor of 10, and with this high statistics, we have been carrying out detailed studies of neutrino oscillations. And I just want to tell you two examples of our updated studies. Well, in 1998, we announced the discovery of neutrino oscillations, but well, this announcement was made based on the observation that muon neutrinos survival probability went down by a factor of 2. But if it is really neutrino oscillations, we should observe this kind of oscillatory behavior. Therefore, we really wanted to confirm neutrinos to oscillate. So, after the initial announcement, we began special analysis to see this kind of oscillatory behavior. In particular, we wanted to observe the first dip in the oscillatory signature. And in fact, in 2004, we published this data. Here I show the oscillation probability as a function of L over E. So this is the long distance, this is short distance. And here you can see a small dip. So this is a first clear evidence for really neutrino oscillations. That was 2004. Another example is the tau neutrino appearance. Well, we concluded that neutrinos oscillate based on the disappearance of muon neutrinos. But if the oscillations are between mu neutrinos and tau neutrinos, one should be able to observe nu-tau interactions. So this is again, this shows oscillations. And in fact, due to neutrino oscillations, some of the neutrinos are nu-taus at the super Kamiokande detector. Therefore, nu-tau interaction produce tau particle, but tau particles soon decay to other particles. Therefore, a typical nu-tau interaction produces a lot of particles, and therefore, well, this already suggests that the analysis may not be so easy. Well, in fact, this is a typical simulated nu-tau interaction event in super Kamiokande. So it's clear that it is not possible for super Kamiokande to identify nu-tau events by an event-by-event basis. Instead, we decided to do a statistical analysis, knowing that nu-taus are upward going only because they are produced by neutrino interactions. So this kind of statistical nu-tau appearance study was carried out, and this is the most updated data. Again, the horizontal axis shows the neutrino direction, cosine Jeans angle, and well, this is the Jeans angle distribution for the nu-tau-like events, and this red part shows the nu-tau component. And statistically, this is already 4.6 sigma effect. And we are happy to say that super Kamiokande essentially observed the nu-tau appearance. So this way, by the way, this was initially presented last year. Anyway, okay, so far I have been mentioning about our studies on atmospheric neutrinos, but well, honestly speaking, there are some other studies. Therefore, I want to mention other oscillation studies. Well, now I want to move on to a completely new topic, that is solar neutrinos. Well, the first solar neutrino experiment was constructed and began operation more than 50 years ago. And this is the first solar neutrino experiment carried out by Ray Davis Jr. and his collaborators. And this experiment observed solar neutrinos, but the observed event rate of solar neutrino was about 1/3 of the predicted solar neutrino interactions. So this is the well-known solar neutrino problem. And subsequent experiments in the 80s and 90s also observed solar neutrino deficit. This graph shows the experimental results on the solar neutrinos. If the experiments observe the flux consistent with the model prediction, then this data should be around 1, but there is a huge deficit of solar neutrino observation. Clearly, these experiments confirm the deficit of solar neutrinos. Oh, by the way, the data shown as a function of the neutrino energy. So, although there were several experiments carried out and confirming solar neutrino deficit, but before the year 2000, we were unable to really understand the cause of the solar neutrino deficit. And the SNOW experiment began at the end of the 20th century, And this is the D2O experiment where they use 1,000 tons of heavy water. By using heavy water, they can observe the electron-neutrino flux, and also independently they can observe the total neutrino flux. That means nu e plus nu mu plus nu tau flux. And in fact, if they observe electron-neutrino flux, the observed flux was about 1/3 of the predicted flux. However, if they observe the total neutrino flux, the observed flux was just consistent with the model prediction. Since the sun can only produce electron neutrinos, therefore the data gave evidence for oscillation of electron neutrinos to the other neutrino flavors. So the long-standing solar neutrino problem was understood to be due to neutrino oscillations. But in addition, I want to mention another experiment related to solar neutrinos. In fact, I'm going to talk about the Kamran experiment. In fact, this is not a solar neutrino experiment. It observed neutrinos produced by nuclear power reactors located in Japan. And Kamran is a 1 kiloton liquid scintillator detector, and they are very sensitive to these antineutrinos from nuclear power reactors. And the data is shown here, and this is again the survival probability of anti-electron neutrinos observed in Kamran. And they saw a deficit of anti-electron neutrinos, and then if they look at the longer distance or lower energy neutrinos, then the survival probability come back to almost unity, then go down, go up, go down. So this is clearly the evidence for neutrino oscillations. And with this data, we were really convinced that solar neutrino deficit was really neutrino oscillations. Now, so far I talked about atmospheric neutrinos and solar neutrinos. Well, since there are 3 neutrino flavors, there must be the 3rd neutrino oscillation channel. In fact, since the early 2000s, I'm sorry, it was the neutrino community's most important item to discover the 3rd oscillation channel. And in fact, the 3rd neutrino oscillation channel was discovered by reactor-based short baseline neutrino oscillation experiments and accelerator-based long baseline neutrino oscillation experiments. And these are the experiments that contributed to the discovery of 3rd neutrino oscillation channel. So, with this information, I think we essentially come to the stage that basic structure for 3-flavor oscillation has been understood. Now, therefore, at this moment, we understood the details of the neutrino mass. But, I have to say, so far, I only talked about results from these experiments, but I didn't talk about the importance of the small neutrino mass. And here, in this view graph, I would like to convince you that we believe that small neutrino masses are very important. First, here, I plotted the masses of charged leptons and quarks. Well, there are 3 charged leptons and there are 6 quarks. And these are the masses of these particles. And now, I think we understood the neutrino masses rather well. Therefore, I try to plot. I try to overlay the neutrino mass on this plot, and they are here. So, first of all, you notice that neutrino masses are well separated from other particles' mass. But please be careful. Well, the horizontal axis, 1 unit is, say, 100 difference. If there is, say, 2 unit separation, that is 10,000 difference. 3 unit separation means 1 million difference. So if you count, then you notice that the neutrino masses are approximately or more than 10 billion or 10 orders of magnitude smaller than the corresponding masses of quarks and charged leptons. 10 billion times smaller. This is significant, and we believe this is the key to better understand elementary particles and the universe. Therefore, we believe studying neutrino masses are very important. Therefore, we want to continue studying neutrino oscillations or neutrino physics, neutrinos. We almost understand what we should study from now on. These are the agenda for the future neutrino measurements. Well, these are the key questions. Well, first of all, we'd like to know the neutrino mass hierarchy. Well, since there are 3 neutrinos, there must be 3 different neutrino masses. And the question is, we do not know if the nu 3 is the heaviest or the lightest. And we do not know if Cp is violated. That means neutrino oscillations for neutrinos and neutrino oscillations for antineutrinos are different. And we think this is a very important question because this observation could be the first hint to understand the baryon asymmetry of the universe. In addition, we'd like to really understand the absolute neutrino mass, and we'd like to know if there's a structure beyond the 3-flavor framework. And finally, we'd like to know if neutrinos are Majorana particles. So these are the main agenda for the future neutrino measurements. But for today, I want to concentrate on the neutrino mass hierarchy and Cp violation measurements in the future. Well, I said in the future, but in fact, if we look at the data from the present experiments, there are already some hints. Well, the data shown here are coming from supercar mu-Cantor atmospheric neutrino experiment, T2K long baseline experiment, and the Nova long baseline experiment. And all these experiments consistently suggest that the neutrino mass hierarchy may be normal, not inverted. And there is a Cp violation, and the Cp violation phase angle is somewhere, well, there. Oh, by the way, definition of the delta Cp angle is different between these 2 experiments, and in fact, the data are just consistent. Anyway, well, these are still suggestions. The effect is only, say, 2 sigma effect or so. Therefore, it's not possible for us to conclude anything from these present-day experiments. Therefore, I think we need the next generation experiments. The first topic is the mass hierarchy. Well, again, to determine the mass structure of the neutrinos is very important. Therefore, there are several experiments proposed to observe the neutrino mass hierarchy. And well, again here in India, the INO project is, well, essentially approved, and we are waiting for the construction, and the experiment began from this experiment. Now, well, many of these experiments are still early stage, but maybe the Juno experiment in China is the leading runner of this measurement. It is under construction, and it will start experiment probably around 2020. Now, another future experiment is the CP vibration measurement. We'd like to observe if CP is vibrated in the neutrino sector, and if this is observed, this is the first hint toward our understanding of the baryon asymmetry of the universe. However, these are difficult experiments, and we definitely need the next generation long baseline experiments with much higher performance neutrino detectors. And in fact, there are two large projects. One is ongoing, another is waiting for the approval. Anyway, both of them are long baseline experiments, and one uses liquid argon detector, and another uses huge water length detector. And well, we hope that these experiments began taking data in the late 2020s. Okay, let me summarize. Atmospheric neutrinos were observed in 1965 for the first time. Since then, there was not much progress for some time, but unexpected muon neutrino deficit in the atmospheric neutrino flux was observed in proton decay experiments in the 80s. And subsequently, in 1998, Super Kamiokande discovered Neutrino Oscillations, which shows that neutrinos have mass. And Neutrino Oscillations were observed in solar neutrinos as well. And since then, various experiments have contributed to neutrino oscillation studies. And finally, the discovery of non-zero neutrino mass opened a window to study physics beyond the standard model of particle physics. And in particular, neutrino physics might be relevant to fundamental questions in the universe. Okay, that's all. Thank you very much for your attention.